Okay, so now we're doing some more definitions here. We're going to be looking at energy and some aspects of how we use the energy inside our bodies. And the type of energy we're most concerned with is chemical energy. Now, in this picture on your screen, you see a dam holding back a lake of water and forming a lake of water by holding the water back, and yet there's some water that's pouring through the dam. And this really defines our two energy terms, kinetic energy and potential energy. You've probably utilized those at some point in your life and heard about them in high school. Kinetic energy is the energy of motion. It's the classic definition. What would it be in this picture? Of course, it would be the water rushing through the dam. And potential energy is the energy of rest, if you will, and that's the energy in the lake. That's what we can access, right? That potential for energy to be released. But again, the term we're most interested in is chemical energy. And so chemical energy is the potential energy that we store in bonds. Work hard to remember this. The energy we're concerned with and that we're going to store away, we're going to do that by and accomplish that by forming bonds between different atoms and different molecules. Okay, and to form bonds, remember the union of electron structure requires energy. We must input energy for two reactants, right? These two atoms or molecules that we want to interact with each other. We term them as reactants. And then when they interact with each other and form bonds, break bonds, do whatever, then they're going to result in the formation of what are called products. So the reactants are on the left side of this figure here, and you can see that in a normal situation without any aids or help or whatever, we have a fairly steep mountain, a fairly large amount of energy that we have to overcome. I always like to liken this to riding my bike, right? So to ride my bike, I've got to ride it up the hill, up the mountain, if you will, and then I get the big whee and I release all that energy. But I had to input a lot to go way up that mountain. Now, what we're going to start to address, especially when we get to proteins, are the existence of molecules that help speed up reactions occurring. And these molecules are called catalysts. Specifically, the proteins we'll be looking at that provide this function of catalysis are called enzymes. So when you introduce a catalyst, it's going to help the reaction occur more favorably, and we'll talk about that more in a few lectures here. And because it's going to occur more favorably or more readily, the mountain decreases. So I get to push my bike up now a much smaller hill, and yet I still get a very nice whee down the hill and still get the release of energy, and everything's great, right? And I get my products. So activation energy is decreased by the introduction of catalyst or enzymes. Now, besides energy, we want to start addressing organic compounds and inorganic compounds. Inorganic compounds are those that are found with, say, carbon monoxide, right, is an inorganic compound. Methane, CH4, is an inorganic compound. It has carbon, though, so why isn't it organic? Well, to be organic requires just a little bit more than just having carbon. It also requires the presence of some oxygen and most likely hydrogen. Without carbon, hydrogen, and oxygen present, we won't deal with anything that doesn't have that, at least, and thus we must call it organic if it has carbon, hydrogen, and oxygen in it. Now, carbon, even though it's not sufficient all by itself to be labeled as an organic compound, we're still really interested in it because it's still a requirement. It's one of the three, right? Must have all three. And carbon always forms the backbone of all these organic compounds we're going to be talking about. And so carbon is unusual. Remember, its breakdown is that it has 4 valence electrons and 4 valence, a valence number of 4. So it has 4 holes in its outer shell that we need to fill. And because of that, it loves to bond. It has these great properties where it loves to form at least 4 bonds. And so carbon in these long backbones that it can form single bonds with itself and form these incredibly long chains of carbons. It can form into branches where we have a long chain of carbons, but coming off that are other chains of carbons, and those are called branches. And it can also form rings, commonly 5 carbon rings or 6 carbon rings. And so carbon is very unusual. It can also double bond with itself, forming a bond of 2 electrons, right? An interaction of those 2 electrons to help fill its outer shell. But what also lends a unique characteristic to organic compounds that possess these chains of carbons is that they often form interactions with certain groups of molecules called functional groups. And the first of these functional groups that are commonly found associated with any organic molecule or any carbon chain is the hydroxyl group. And we've already talked about hydroxides, OH negative, when we were discussing pH. And so this OH can be attached to the end of a carbon chain. And when it is, it's typically referred to as a alcohol. Okay? Also, we'll see this with many sugar groups, and we'll be talking about those in the next video. Another common group attached to the end of a carbon chain is a methyl group. We'll see this quite commonly. And methyl groups are CH3s. Why not CH4 like in methane? Because remember, we've got 1 bond attaching to the carbon chain. The other 3 of the 4 bonds will be filled by hydrogen molecules. The third major functional group is called a carboxyl group. We'll see this in many of the most important molecules we'll be discussing about, most important organic molecules. And it's composed of a OH group, a hydroxyl group, but we're going to throw in another hydrogen, a double bonded hydrogen. So we have a COOH, and that's called a carboxyl group. And we'll see those in all fatty acids. We'll see them in proteins. We'll see them in many places we'll be talking about. The fourth molecule here is an amino group. The amino group gives the amino acids their name, right? So amino acids are going to be found, as we'll see, in proteins. And what we have is an N, a nitrogen, with a couple of hydrogens attached to it. The third bond of the nitrogen is attached to the carbon chain, or carbon molecule. And finally, the last major group, one that will probably affect you the most significantly in this semester and indeed throughout A&P2 as well, is the phosphate group. And the phosphate group is a central phosphorus atom surrounded by 4 oxygens. And so those will commonly be found in nucleic acids, but most importantly in the molecule that we'll be talking about a lot here in a few lectures, adenosine triphosphate, or ATP. So the energy that we're going to be using, since we've talked about organic compounds, what are we going to be using this energy for? Well, we can use this energy to form bigger compounds. We can take these energy-poor molecules and we can add more molecules to them, and we're storing the energy in the bonds between these energy-poor molecules. So we can start to hook up some energy-poor molecules, dump energy in there, and we will form these larger energy-rich molecules, because now the bond that holds these energy-poor molecules together have lots of energy in them, making now this bigger molecule energy-rich. This is called a polymer. So we take basic units called monomers, typically fairly energy poor, and we add one monomer to another, and we get a polymer, right? As we begin adding more and more monomers, which are single, mono, single, poly, many, we add them together to form these larger molecules. This process of forming larger molecules from single energy poor ones is called dehydration synthesis, most commonly, or you may hear it called condensation. Aha, you say, condensation. I know that. When I go out on the lawn in the morning, I see water or dew, or condensation. So I can think then in this term that what I'm doing here is producing water. And that's exactly what's happening. You can see that my monomers will have these simple OH groups that are protruding off of them. And by liberating the OH from one monomer and a hydrogen from the other, I create water. And by liberating those groups, I create the water and I provide a extra oxygen for bonding to occur, forming this so-called dimer. Right? And as I add more and more of these energy poor groups, I'll form a polymer. Dehydration synthesis is the set of reactions that will always be used to create energy-rich polymers from smaller energy-poor monomers. So if we form these big molecules and we've got all this energy stored in these polymers, we're going to do this at times of the day when we're not utilizing energy. Perhaps we just ate, so we've got all these energy-poor molecules that we're going to put together into these long strings called polymers. But at some point we want to access that energy. When we're running, when we're busy, when we're thinking, we want to break down those polymers. And to break down those polymers, we need water. And we're going to put water into this system. So by adding water, we're going to create those two OH groups again and break that oxygen bond that was holding those two monomers together. So we take the polymer, we break it down, or in this case, as shown on this picture, the dimer, we break it down into its two subunits of polymers. And so we're breaking that bond, we're liberating the energy. This set of reactions is called hydrolysis and requires water. So dehydration synthesis takes small energy-poor molecules, makes larger energy-rich polymers, and liberates water in the process. Hydrolysis requires water to separate the smaller subunits or monomers into their individual components.